Seeing Interstellar in IMAX on opening night will always stay with me as one of the great experiences of my life. The journey we were taken on was so epic and profound in this movie, with so many extraordinary moments that I'm not expecting another film to equal it in my lifetime. There is so much one could talk about when it comes to Interstellar, from the outstanding performances, notably Matthew McConaughey as Cooper at the peak of the reconnaissance, to the music that might just go down as Hans Zimmer's greatest. It is all around an extraordinary experience. But one of the most important aspects of this movie, and why it has so much emotive power, is how it makes use of scientific reality. It is important to note, first and foremost, Interstellar is a movie, and telling a compelling story does take precedence over keeping the science 100% realistic. But even with that, when it comes to the science, it does something that I'm not sure any other film really has. The genius of the storytelling is that it makes the physical reality of relativity an emotional device that affects the characters and the story of the movie, and therefore it affects us and makes us care about it and be moved about it in a way that most of us lay people never had before. But if you're anything like me, you likely accepted the reality of relativity whilst not really understanding it in any meaningful way. And not being a scientist nor mathematically minded, I really thought it was beyond my capacity to grasp, having made several unsuccessful attempts to do so. However, one fine day, when I was reading Walter Isaacson's splendid biography of Einstein, and specifically the section on the special theory of relativity, something in my mind seemed to click, and I suddenly understood it. From there, I spent a few months studying and managed to gain a pretty basic grasp of it. But what I realized is that these things are possible to understand conceptually without need of any math. Now, the most important thing to accept is that relativity is not difficult to understand conceptually. It's simply that it does not conform to our intuition. And overcoming this is what makes it so challenging to grasp, rather than the physics itself. So before we really get cracking, there will be a little bit of history, followed by 3 thought experiments. Each one builds on the other, but please feel free to pause and rewatch each one as needed. The key is that all 3 combine to offer an explanation, so don't feel that you should have a grasp of anything after watching any of the explanations in particular. Okay, are we all set? Let's science. Now, as we all know, relativity is the brainchild of Albert Einstein, one of the greatest scientific minds in history. What is so compelling about Einstein is that his greatness was not to be found in his mathematical ability, nor the quality of his experiments, etc. No, rather it was found in his creativity, and his ability to follow his theoretical leaps to their inevitable conclusions, even when they completely undermine the very foundations of accepted science. And rather than spend his days thinking about equations and formulae, Einstein would imagine scenarios and experiences and ponder their implications for physics. For example, we know that when we see an object, what we're perceiving is the light being reflected off of it. Even though light travels extremely quickly, 299,792,458 meters per second, it takes time for that light to bounce off that surface and reach our eyes. This means that we're technically perceiving the world in the past, albeit the very, very recent past. From this basis, Einstein considered what he would experience if he was on a train departing Zurich station at the speed of light. If he were to look back at the face of the station clock, what would he see? As we said before, it takes time for light to reflect off of a surface and reach our eyes. So if the train is departing at the same speed as the light that's being reflected off of the clock, no new light would ever be able to reach the train. And from Einstein's perspective, both the clock and time itself would appear to have stopped. Now, clearly this doesn't make sense, but Einstein would be the first person to figure out why it doesn't make sense. But it's these kinds of things that Einstein engaged in to stimulate his creativity and drive physics forward. And his genius lay in the ability to think through them and analyze them without any of the baggage of classical physics clouding his mind. Now, ever since Isaac Newton's extraordinary, groundbreaking, and perhaps unsurpassed work in understanding the physical world with his laws of motion and universal gravitation, There had been an assumption that was completely taken for granted ever since, that time and space were absolute. What does this mean? Well, it was a given that both time and space were the same for everyone and everything, everywhere. They were consistent all throughout the universe. It was thought that there was a kind of grand cosmic clock that was ticking time forward at a constant and consistent rate for the entire universe. And because motion was absolute, it meant that there was some sort of absolute stillness against which everything was either moving or not. Now, in order for this to be the case, scientists postulated that this must mean that there was a substance dubbed the luminiferous aether, which was omnipresent throughout the entire universe, and this was the aforementioned cosmic stillness. This substance had to exist because, for example, light waves had to have something to propagate through, similar to how sound waves travel through air. And for all of this time, scientists were coming up with ever more ingenious ways to detect the aether. But much to their chagrin, there did not seem to be a trace of any such substance anywhere. Now, in 1887, Albert A. Michelson and Edward W. Morley performed the famous Michelson-Morley experiments. Their objective was to detect differences in the speed of light due to the motion of the Earth through the supposed aether, therefore proving its existence. But instead, their experiments proved the exact opposite. Light moved at the exact same speed, fatally undermining the aether hypothesis. The speed of light was constant, and this is one of the first components of relativity that really does run contrary to our intuition. And with that, we are going to begin our first thought experiment. Now, as an example to explain what this means, we're going to use some cars on the road. Now, if you are in a car parked at the side of the road and another car drives past you at 20 miles an hour, it is moving away from you at 20 miles an hour. Basic. If you are driving at 20 miles an hour and a car overtakes you at 100 miles an hour, it's moving away from you at 80 miles an hour. Now, if you are driving at 50 miles an hour and a car drives towards you from the opposite direction at 50 miles an hour, it approaches you at 100 miles an hour, and once it passes you, it moves away from you at 100 miles an hour as your two speeds combine. What Michelson and Morley demonstrated is that light does not behave like this. No matter whether you are traveling at 10 miles per hour or 10 million miles per hour, light will always move away from you at 299,792,458 meters per second. To put it almost too simply, if light were a car traveling at 100 miles an hour, it would always move away from you at 100 miles an hour, whether you were stationary, doing 20 miles per hour, or 99.99999 miles per hour. However, ironically, the laws of relativity mean that I cannot demonstrate this in an animation. Now, the reason this is the case is that the speed of light is constant. This is why it's denoted as c. And it is time and space that change and warp around that constant. They are relative, but don't worry, as I said in the intro, this does not need to have clicked yet. Despite there being absolutely no evidence whatsoever to support the existence of the aether, almost no one was able to discard it as a hypothesis. While there were scientists like Lorentz and Poincaré who seemed to doubt its necessity to explain the things that they were involved in, Einstein really was the first to completely discard it and ask the fundamental questions of how the universe might actually look in its absence. In order to understand what this means, it really is very, very straightforward, honestly. And in true Einsteinian fashion, we will demonstrate why with another thought experiment. I want you to imagine you are walking up a hill. And once you get to the top, you stop. Look around, admiring the view. You look up at the sky and notice that a spacecraft has parked itself just outside of Earth's orbit and is looking down at you. As you're both stopped looking at each other, are either of you in motion or at rest? Well, you're standing completely still. So obviously it's you who is at rest and not moving. Besides, you can see the spaceship slowly moving across the sky. So obviously they are in motion. But now, if we swap to the perspective of the spaceship, they are stationary, parked up, looking down at you standing on a planet that is hurtling through space at 67,000 miles per hour. So clearly, it's the spaceship that is at rest, and it's you who are in motion. The fundamental aspect of relativity that needs to click in order to grasp it is that both of these perspectives are equally correct. This is not a challenging concept to understand, but what makes it challenging is grasping why this is a scientific reality rather than simply a philosophical one. Why does understanding motion in this way mean anything? Why does it matter? In order to understand why and what this means in practice, let us consider Einstein's special theory of relativity. The special theory applies to the special case of uniform motion at a constant speed, meaning it applies to an idealized scenario that would likely never actually exist outside of a lab, of an object traveling in a straight line at a constant speed. There are no changes in direction or how fast it's traveling, making it much easier to consider and, crucially, easier to grasp. Remember, although it's something we all take for granted, the laws of physics are identical in all frames of motion. This means that, for example, whether you are sitting in the back of a moving car or standing still atop that hill, if you throw a ball straight up, it will fall straight back down. Now, onto our third thought experiment. We are going to introduce our observers, A and B. Now, what is an observer? It's simply a perspective that we have chosen to analyze and measure the universe from. Somewhat confusingly, the word observer doesn't refer to a conscious being or something that can see. Rather, it is simply a perspective that we have chosen to observe from. An observer could just as easily be a rock or simply a point in space 10 billion light years away. Now, observer A is on board the train and observer B is outside the train. Okay, we're all set. Are you ready to understand relativity? Let's go! As observer A is sat in their seat inside the carriage, they decide to shine a flashlight straight up towards the ceiling. Now, from observer A's perspective, the emitted light is traveling up in a straight line between point X and point Y, as one would expect. But what would observer B see when looking at the same flashlight only from outside the train? Now, of course, observer B would be stood still on a platform, say, but we're going to demonstrate it like this for ease of explanation. Now remember, as Michelson-Morley demonstrated in 1887, the speed of light is constant and is the same for everyone, regardless of how fast they are moving. So even though observer A is speeding along in a train and observer B is not, the light emitted on board the speeding train travels at an identical or constant speed for both of them. So, as observer B looks at the same flashlight emitting the same light moving from point X to point Y, they see something a little bit different. Now remember, it takes time for light to travel between 2 points. So unlike observer A, who sees the light traveling straight up with inside their inertial frame, or the train, observer B sees the same flashlight moving forward through space. So by the time the emitted light reaches point Y, point X, or the flashlight, has moved forward through space and is now at a different point in space. Remember, both observers are perceiving the same event. It's simply that they are doing so from two different but equally valid perspectives. Whilst observer A sees a straight line between points X and Y, observer B sees a diagonal line between those 2 points. Obviously, in any real scenario, the variation would be extremely slim, almost impossible to measure, and this is exaggerated for the purposes of demonstration. But inevitably, any diagonal line means that there's a greater distance to travel between the 2 points, because obviously a straight line is the shortest distance between 2 points. But hang on, if light travels at a constant speed for both of them, but observer B perceives that light traveling a greater distance to go from point X to point Y. Wouldn't that mean it would also take more time to do so? Well, the answer is yes. As we have hopefully just observed, it's the speed of light that remains constant in all perspectives, while space and time are what change and warp to accommodate it. In other words, it's not light that bends to fit our reality, it's reality that bends around light. The same event takes a greater amount of time for observer B than it does for observer A. And this effect is compounded as the train gets faster and faster, relative to observer B, who is stationary outside of the train. And this, in a nutshell, is relativity. Now, as I said before, special relativity deals with uniform motion, beautiful straight lines with no curves and, crucially, no gravity. The physics of Interstellar is orders of magnitude more complex and more difficult to grapple with. So I think I might need a bit more practice before I even think about attempting a video on that. If I'm even capable of it, of course, not being a scientist. But either way, I hope you found this extremely simplistic explanation of special relativity interesting, and that maybe this mystery is a bit easier to grasp. So please watch and rewatch as many times as you find useful, if you find it useful at all, as this is a very counterintuitive concept to understand, but it will click. And when it does, go back and watch Interstellar again. Well, if you've made it this far, I want to thank you very much for watching. I hope that you were able to get something out of this video. I had a really great time making it. It was really difficult, but it was also really fun. I love making animations and stuff. Let's head down to the comments if you've got any memories about the science of Interstellar and how it impacted you, you know, the time dilation and everything like that. I still get my mind blown by just how amazing of a job Nolan and the team did in exploiting scientific reality to tell an emotionally powerful story. So yeah, definitely share your memories of that in the comments. And if you did get anything out of the video, please consider clicking like, as it does help me a lot and I'd really appreciate that. Thank you very much. And if you'd like to see more videos on cool, awesome stuff, please consider clicking subscribe as well. But other than that, I hope you have a wonderful day. I want to thank you once more for watching, and I will see you in the next one.